Okay, I wanted to start with a little announcement, which we talked in the beginning of the class about the importance of knowing the greats, who are the founders of computer science. And I think it's a very good opportunity now to talk about one more person who everybody should know, and all of you should read at least one of his papers. I think it's necessary. This is Leslie Lamport. And the reason for this occasion is that yesterday he was awarded Turing Award, the highest award in computer science. Again, I think that it's one of the cases where it's sort of clearly well-deserved and long overdue. He should have gotten it, whatever, long time ago. He is one of the founders of the science of distributed computing. So those of you who claim any expertise in it, and I know that some of you do, should take care and go and study his work. Some fundamental things like Paxos, things like sort of the general theory of causality, the programming causality, the time intervals and things like that. He did, and again, I highly recommend that you go and read at least some of these papers. Okay. So let us now go back to the course. We looked at the benchmarks last time. There were several comments to which I want to address. Some people were saying that, well, I could improve on your algorithms. Maybe yes, maybe no, meaning that these were unspecific statements. For sure, I can improve on these algorithms. That I do know. But you see, we were not trying to write the best possible sort. In some sense, my goal was to write a plausible sort. Let me define the plausible. The shortest sort which will run as fast as the one in the standard library, right? At least for randomly shuffled integers. And as you saw, we accomplished that. The second thing, it should be relatively small and easily translatable into other languages. Again, these were requirements. Again, these were not an attempt to write the most sophisticated sort. Maybe at the end of this course we will do that. But that was not the point. The point was to write some simple code, relatively simple, and compare different languages. Again, I claim that this was a fairly careful thing. In a sense, we did not try to write code in a way where one of the languages will be in a disadvantage. The C++ was written in a very, very simple way. Again, it was fundamentally C code, without any specific C++ things. We tried to write Java very well. We did not try to write Java so that it will underperform. Again, we submitted it to a bunch of Java guys. Nobody suggested any specific improvements. And again, we wrote Python, and at least one of us, not me, is a very, very experienced Python programmer with 15 years experience in Python. He thought it was a very plausible thing. So again, I apologize, I'll just turn it off. The point was that what we're trying to measure is if a competent programmer writes something in one of these three languages, what are the performance things? And without claiming that we're the best programmers, we're pretty close to like being good programmers, right? So that's just some explanation of what we were doing. Then we started looking at sort and compared, if you remember, stable sort, partial sort, source-harm discrepancy. There are many more things which we will do there. But just for a time, we're going to abandon it and look at a slightly more general problem and try to compose a somewhat even broader benchmark. For that, I have to step back and look at the situation in programming, how it developed. You know, I always take historical. Those of you who know me know that I always try to take historical approach. In case of programming, again, a lot of my approach was influenced by my friend Paul, who is a great historian of software. Sort of let us go back and look how programming styles developed. We know him. So let us look how programming styles developed. Okay. If you remember, the first programming language was Fortran. So in 1956 or 57, it came out, and very quickly, large set of libraries, you could get rid of Leslie. We talked about him. Well, I didn't mean him, but yeah. Oh, very quickly after Fortran appeared, many physicists started writing code, and that led to a remarkable fact that within, say, 10 years, they created large body of Fortran libraries. Again, so the Fortran became successful not only because it allowed people to program faster than assembly language, but because it allowed the creation of portable libraries which sort of would speed up the task of whatever physicists were doing. So it created libraries, but these libraries were fundamentally numerical libraries. Fortran was numerical language. If you wanted to multiply two matrices, there would be a library procedure for doing that. If you wanted to find shortest path, say, most likely, at least at that time, it wouldn't be there. What happened at the same time was several other programming languages appeared, mostly in academia, who started spreading in academic circles and claiming certain greatness. One of them sort of originated in Dartmouth. Where was McCarthy? No, he wasn't at Dartmouth. He was at Dartmouth. He was at Dartmouth. But then he moved to MIT, where he, sort of with the help of his students, produced a language called Lisp. In particular, Lisp, which dialect of Lisp? 1.5. This is 1.5. It's the thing to remember, that Lisp starts with Lisp 1.5, and eventually sort of there is a long and sort of bushy tree of different Lisps, sort of which come from Lisp 1.5, and one of them is MacLisp, sort of MIT dialect, and another very important dialect which was developed here was called, well, Sail was the Stanford thing, but then Xerox PARC developed Interlisp, which was a major dialect of Lisp. And the claim was that somehow Lisp was the way. Okay? Some of you, Nick, probably was exposed to this idea that Lisp is the way and could solve all problems. It was not the only language which claimed to solve all problems like that. Another language, which appeared slightly later, but roughly within the same time frame, was a language developed by a certain assistant professor at Harvard, who published a book called A Programming Language. Anybody knows what the language was? APL, A Programming Language. And the person's name was Ken Iverson. Again, sort of while we're talking about Turing Award winners, there is a very, very important paper, Turing Award speech by Ken Iverson, he won Turing Award, entitled Notation as a Tool of Thought. Because you see what happened is that all these people who were inventing these academic languages or interesting languages, being McCarthy, being Iverson, being later on another fellow, sort of, it's not clear whether he invented the language, but he got the credit, a guy from Xerox Spark called Alan Kay. Smalltalk. So all these people claimed that there was something wonderful about their language which solves all the problems. In case of Iverson, he claimed that the greatness of his language was the notation. Notation as a tool of thought. Those of you who see an APL, it's a bunch of very bizarre, totally incomprehensible notation. But he claims that is the strong point. Of course, McCarthy also claimed the greatness, first of all, because he claimed that it had beautiful syntax. Everything was in parentheses, everything was an S expression. Whether it's beautiful or not, it's in the eyes of the beholder, but it also was functional. So again, its greatness was because it was functional. And then Smalltalk, of course, was great because it was object-oriented, whatever that means. These languages indeed demonstrated one thing. They demonstrated that you could create certain non-commercial software, usually the software which was not good for prime time, but you could create it fast. Right? For example, there were people on Wall Street using APL for financial simulation because they could do things fast. There were people in AI community who claimed that they could develop symbolic algebra system fast because they used Lisp. And in case of Smalltalk, I do not know what you could develop there. There are hardly any examples, but they claimed that at least children could comprehend computing much better with, yes?
Havea simulators are developed on Smalltalk.
What kind of simulators?
Havea, I mean aircraft simulators.
That might be true, but it's not what I know. I used to work for a company called Silicon Graphics, which was one of the leaders in providing simulating hardware and software. The interesting fact, it did not support Smalltalk, in spite of having total lock on the market. Do not believe everything you read. Maybe in Russia. And indeed, Russia is doing all kinds of things. In Russia, by the way, they were using a great language of that generation called Refile. In Russia, they did not use Smalltalk or Lisp at that time, long time ago, before you were born. But again, the claim that if you wanted to do the sort of advanced computing, you had to use a language called Refile, R-E-F-A-L, developed by Valentin Turchin, which again was based on Markov algorithms, certain notation for. And again, the claim was you could produce some wonderful things. Now, sort of, the question is why these languages were successful. Was it their notation as the case of APL? Was it the beautiful syntax of Lisp, and its functional nature? Was it object-orientedness, which in Russia they used to build their planes, or whatever? Or was it something else? The interesting fact that these three languages are utterly different in terms of, in terms of the syntax, semantics, everything. But they had one thing in common. Anybody would venture to guess? They were interpretive, and how would you, sort of, what is the most primitive thing in APL? Oh, nobody knows APL. Well, again, it has these built-in matrices, right? It has this fundamental data structure which is sort of allows you to write things. And people learned, say on Wall Street, to reduce everything in the world to matrices, and there was extensive libraries of matrix-like algorithms, not Fortran style, but for doing all kinds of problems. Again, it was ability to use these extensive libraries. The same thing in Lisp. Of course, the proponents of Lisp claimed that the greatness of Lisp was because it has cons. But actually, no. The greatness of Lisp was it had an extensive libraries, which allowed you to append to things, reverse things, sort things. Again, it was not a very well thought through library. Okay, you could say, how would I dare to criticize? Okay, let me dare. Let me give you an example. For example, the great people who produced Common Lisp forgot to put binary search in it. Right? Sort of, they have a very comprehensive, they think, library of sequence operations. Of course, they do have sort, but they don't have binary search. They never figured out how to put it there. It lacks it. And I would say that binary search is a fundamental algorithm. Nevertheless, in spite of not being very well thought through, it had a large body of things so people could put things together quickly. Again, Smalltalk also had a bunch of things, and in many respects, one of the most comprehensive things, not very well thought through. Again, many algorithms are missing, many data structures are missing, but it had sets and maps, things which you use now, for example, in all these languages, sort of go back to Smalltalk. It also included things dealing with windows, which at that time were very, very important if you wanted to put an application together. So what I claim is exactly these libraries which made these languages so productive. But of course, even having these libraries and making programmers effective, and even making totally inexperienced programmers effective. Again, you could take an MIT undergraduate, and with all due respect to MIT greatness, MIT undergraduate is not really a good programmer. You could ask, am I correct? He might think, they do think they're great programmers, each and every one of them. I had many interns from MIT. It's very hard to deal with them because they say, oh, we took this course, it used to be Scheme course, now it's Python course, and they know everything. They're very opinionated. But they're actually not good programmers at all. But again, if they deal with these languages, they could quickly build something up. It does not require much. But then what happened was that in spite of ability to produce applications quickly, none of these languages became successful. Not commercial. Well, actually commercially and non-commercially. It's not just that commercially successful, but even in what it's called, Lucini's, there is a term, open source, even in an open source community. These people could do anything they like. They could write all their code in Scheme, right? But they don't. Because if they do, nobody will use their stuff. That's so they discovered. Right? So we need to understand why it happened. And I claim that the fundamental reason that it happened, and you will see eventually how it all lead to what we do, is that in spite of all the claims of their proponents, you cannot make these programs effective, efficient. They were way too slow. Right? So, of course, people, I mean, some of you might be old enough to remember Guy Steele master thesis. What was his master thesis? Anybody know? Called the Rabbit, a compiler for Scheme. There he made these grandiose claims that you could take Scheme and compile it faster than Fortran. Master thesis. You could make any claims you like. Right? Sort of nobody ever did.
You mean the compiler would run faster than the Fortran compiler?
No. No. The point was that compiler would run very slow but generate this wonderful code. All these closures will sort of be turned into just one instruction. Never happened. Right? It's science fiction. As good as Isaac Asimov or whatever. So there were claims that you could make them efficient, but these claims never became a reality. So, and the fundamental reason for that was that the languages were very far from the hardware. The gap between the sort of imaginary machine, for example, Scheme machine, which needs closures, which needs call with current continuation, which means that you could, it's sort of highly generalized go-to. You could save the full state of the computation, go do something else, and then jump back into whatever you were doing. Wonderful stuff, utterly preposterous. But you know, you could do all these things. Therefore, you couldn't run fast. It was removed from the hardware. Again,
They tried to build hardware.
yes, they did build hardware, and again, some people bought it, like I did. Again, I spent many years, about 10 years of my life, convincing people that Lisp and specifically Scheme was the way. I used to teach a graduate course in algorithms where I would explain to my poor students that they should forget all this Fortran and C and learn Scheme, because all the commercial software, most of them were working either for Bell Labs or financial institutions on Wall Street, that all the software will be written in Scheme. I could show you the lecture notes are still available. And fortunately, they're not asking for their money back. But they should. Many people, I'm not saying some evil people, I was the evil people. But it didn't work. It was, again, it's this. By the way, it's a very instructive thing how a large community could really believe something which has nothing to do with reality, cannot be demonstrated. Right? But it happened. I was part of this thing. Now, what happens is that, and that's there are many good ideas which came from these languages and from these systems. But there also came certain things which are affecting you now, whether you program in C++, Java, or Python. The problem is that when people were programming in Fortran, they were using very efficient data structure called array. It is very efficient because it maps naturally into computer memory. All the languages which I mentioned, with an exception to some degree of APL, but specifically Lisp and Smalltalk, introduced advanced data structures. I don't know why they are very advanced, but for example, in case of Lisp, the idea was, let us go and use lists as the universal data structure. Of course, both common Lisp and Scheme has vectors, but you don't use them. That's not the primary data structure. The primary data structure is list. And one of the things which we're going to see in this course is that lists are fundamentally flawed. And they are more flawed now than they used to be when McCarthy learned to program. Primarily because lists, if you use them as lists, that is, if you, for example, sort them, when you sort a list, what happens? Anybody knows? You shuffle cells. Thank you. Therefore, what happens if you have a large list? Your successor. You are always likely to be in the cache. It's your successor which is very unlikely to be in the cache. So the moment you sort a list, which if you don't sort it, if you don't shuffle it, why are you using it? Use an array. If you start shuffling it, what you create a data structure which on every advance has a cache miss. We will verify the claims, right? Again, sort of things which came with Smalltalk, things which we take for granted are things like sets and maps. Again, when I look at how you people use C++, for example, when Greg writes his code, he always says set. I'm sure that's what he's typing in now. Again, guys, I think we warned you. No laptops. Yeah, I mean you. But again, so what we got from Smalltalk, we got these tree-like data structures. And they're all kinds of trees. And many of them are very interesting. And, I am partially responsible, for example, for bringing sets and maps into the world of C++. Cannot be denied. They tend to be slow for that very reason. They tend to be cell-based, node-based. Therefore, they are spread all over memory. Therefore, they tend to be slow. So, bringing these data structures leads to the following fact. Everybody starts using them without thinking. Like every Lisp programmer uses lists without thinking. I mean, that's what a natural thing to do. If you start nowadays programming in C++ or Java, you assume that you will just have sets of sets and that's all right. It's not. We shall see that there are sort of consequences. Again, there are some languages which actually sort of literally put these advanced data structures all over the place. Python is an example. But again, there are consequences. Using advanced data structures without thinking leads to enormous performance degradation. You could say, by how much? Well, I actually say that from 1 to 2 orders of magnitude, decimal, 10 to 100 times. And even if you program in C++, right? So unless you use things judiciously, so that's what we'll try to demonstrate. So what we decided to do, Bram and I, is to do the following thing. We decided to write a simple application, very simple. Again, obviously you will say, guys, but our search engine is much bigger. Yes, yes. But we needed something we could show in the class. Something somewhat realistic, but nevertheless doable in the class. So we decided to write it in two ways. One way, sort of using advanced data structures. Another way, not using advanced data structures. And there are issues with both, as we shall see. But that's what we're going to show, and Param is going to lead the investigation. We're going to show you two pieces of code and explain what are the drawbacks of the corresponding ways. All right? So Param will go here. One thing, you have to have a little 10-minute thing, then break.
Okay, so let me first describe the problem we want to solve, right? Let's say we have some piece of text, and we want to count bigrams. Let's say we want to print out the most common 250 bigrams in that piece of text. So what is a bigram? A bigram is a sequence of two words that are adjacent to each other. So for example, let's say we have the sentence, Amazon is a great company, right? So that's 5 words. 5 words means 4 bigrams because there are 4 pairs of adjacent words. And in this case, the bigrams we have are Amazon is a great and great company. So we have 4 bigrams, right? So what we want to do, we have some large body of text. I have to keep my mic here. And we want to find out, and so of course bigrams repeat a lot if you see language. And so we want to see, okay, what are the common bigrams in that piece of text? And this is not an NLP course, so we are not, otherwise we wouldn't be teaching it, of course. So we are not doing any normalization. We're not going to lowercase our words. We're not going to do anything special with punctuation. As far as we are concerned, a word is a sequence of characters that are not white space. And that is it. There is nothing more to it. That is a word for our purposes, right? You can make it more elaborate if you want. Okay, so let's see. We want to count bigrams. How would a modern programmer think about this, right? We scan our text, we read bigrams, and we want to count them. So we need some kind of map that we update. We read the bigram, we increment the counter, and at the end we have a count of all our bigrams. And then we need to find what the most common ones are, right? So let's see. What are the data structures we need? We need a map that goes from bigram to count, right? So we need to decide, okay, what is this bigram thing? How are we storing a bigram? And we know that words repeat a lot, so you don't want to copy the words. So let's say we keep a set of words, and we represent a bigram as 2 pointers into that set, right? So basically a bigram is a pair of, what in C++ STL notation you would call an iterator. So a bigram would be a pair of iterators into the set of words, right? So we read our word, we see if it's in the set or not, we create a bigram, we update our map, and so on. And at the end, once we have the entire map, we need to find what's most common, right? So again, we don't want to copy things, right? So we'll just create another set that contains pointers to the bigrams that we've created before. So pointers to entries in the other map. And here we'll have a custom comparator that compares using the count. And so we just iterate over this, insert into this, and at the end we've got an ordered sequence of bigrams. We can iterate over that and get our most common, right? Very straightforward. So let's look at the code for it. Yeah.
The last set is not a set. It's an ordered list.
Well, a set is In C++, STL, a set is an ordered container. It's implemented using a B tree, typically. A red-black tree, sorry. Yes, red-black tree. And as is this map thing, which is also a red-black tree. And of course, this is also a red-black tree. And the good thing about trees is when you insert into trees, the iterators that you already have are not invalidated. So you can actually do this thing. Otherwise, you'd be in trouble, right? All right, let's look at the code.
Is there a reason why we didn't choose to go with hashing here?
Map is 3 letters. And hash map is so much longer. Why would you use something more complicated? Plus, it's not there in C++ 2003, which means clearly, they meant us to use a map. I mean,
Well,
I'm just
you
using what's in the
could,
language.
And you could, again, sort of for this set, you obviously cannot use a hash set. You need ordering. For the other one, you can, and we could try, and we could see what is going to be the difference.
Yeah, I mean, I think that would be a good thing to try. It would probably be a little better, but I don't think it would invalidate the basic. We'll see.
Let us wait and see.
Yeah. All right. So the file is called smalltalk.cpp. Okay. So the basic data structure. Again, we're going to put our words in a set of strings, right? And the basic way we represent a bigram is the bigram has 2 iterators, 2 sort of pointers into the set of strings, first and second, representing the first word and the second word. And of course, we are going to put them into maps, and also we need to be able to compare bigrams. So we have a less than operator defined, which compares the first word. If the first word is less, we are less. If the first word is greater, it's greater.
Just to point to this little thing, string there. It's a string. This is not sysstring. This is some heap allocated thing.
Yeah, let's not think about performance right now. We are just doing it in a straightforward way.
I'm just pointing what is going on. This is a
Once
string.
we are done with both pieces of code, I plan to actually draw what the links are, and then you will see in much more detail what is actually going on in memory. And that is actually very instructive. OK, so if the first word is less, we are less. If the first word is greater, we are greater. Otherwise, we compare the second word. So straightforward, right? OK, now let's go to the main program. So words is our set of words that I described over here, right? This is the map of bigrams that we will update as we read our file. OK, we check our arguments. We open our file. OK, and then we need to keep track of the previous word that we read. So read next word from file. Set has a very useful function called insert, which has very nice semantics. So if you call insert with a word, it returns a pair. The first element of the pair is, OK, so if something was inserted, the first element is iterator to what was inserted and true, saying, yes, we did insert. If the word already was present in the set, we get back an iterator to the old word and false, saying nothing was inserted. So this is perfect for our purposes. We don't really care whether we inserted one or not, right? We just want to find, insert it if required and give me a location, right? So we just say words.insert word.first. This gives us the iterator that we need to put in our bigram. And then if we had a previous word, so if it wasn't this end value that we had set before, we increment the count of this byte. So this is actually probably worth spending time on. This is a cute way of initializing our bigram, because you can use any struct can be initialized with curly brace a comma b comma c. This is what I'm doing here. It's just previous iterator, current iterator with curly braces around it. In C++11, I don't know if it works in previous versions, but certainly in 11, you can use the unified initializer list syntax to do it this way. It's cute. And plus plus counts, you have your map, no problem, right? And we update previous. So that's our main loop, you know. Any questions? No? Trivial. Okay, now here it's a little complicated, right? Now we need a set of iterators into our previous map, which was bigram size. And now we need a custom comparator because we need to compare, you know, we need to dereference our iterator, we need to pull the count out of it, compare that, right? So let's take a look at what this compare bigram count is. All right, here's compare bigram count. You can see this is actually totally similar to the way we were comparing bigrams, right? So we get two iterators, that's what we are comparing. We dereference, second was the count, because first was the bigram, second was the count. So we compare counts first. If the counts are ordered, we know which way to order it. If not, we compare the bigrams, and so basically this will implicitly call that and compare the bigrams, and so you have a complete order in the set, right? Total order is the technical term, as Alex points out. So we just iterate over our counts map, throw everything into our sorted bigrams set. You know, when we're done, we say, okay, start at the end, you know, go back and print out as long as, you know, your counter is less than 250. That's it, very simple, less than 100 lines of code, right?
Food. Food. F-O-O-D.
Food. Okay, let me just show you that it does compile, and then we can eat. That's very important. Did I write? I need to do that. It compiles. For our data set, we are using the complete works of Shakespeare. So I will now run this on the complete works of Shakespeare. So it runs quickly enough. It's unfortunately in the opposite order. So let's start from. Yeah, so the most common is I am, you know, in the, I have, of the, you know, all of that. Yeah. Yeah, as I said, not an NLP class. And it takes 2.24 seconds. Pretty fast, right? 2 seconds.
That's a single time. It's not cache.
Yeah, so I mean, we don't want to measure disk speed here. We're not, you know. So we do want the cached value. So 2.2 or so is what it costs, right? Okay, so let's have lunch, and then after that we will look at the other version.